The third part of this lecture is concerned with weak stochastic Runge-Kutta methods. In weak approximations to SDEs, the interest is not in the solution trajectories as such, but the distribution of them. In this case, we replaced the weak Ito-Taylor approximation by a Runge-Kutta style approximation, which avoids the use of derivatives in the drift and diffusion coefficients. The reasoning behind this is very much the same as for strong stochastic Runge-Kutta methods. In this part, we consider a rather general class of weak order 2.0 methods by Andreas Dressler. Similarly as in the previous section, we present a table formulation for the methods. This makes it easier to present the rather complicated formulation of the stochastic Runge-Kutta method. As you notice, the higher order method now requires a more complicated table formulation. The table values are then used in combination with this type of a sum construction, where evaluations of the supporting values are done for the drift and diffusion models. The supporting values are required to be calculated through the use of the table values, and in this higher order method, even these become quite complicated. The weak order schemes are, however, quite nice to work with because the double Ito integrals are now easier to work with. In the weak schemes, we can use the following approximations for the delta beta values, even if I and j do not equal each other. Here only 2m minus 1 independent random variables are needed. And this means that we run into no such problems with the cross-term integrals as we did in the strong Runge-Kutta methods. For example, we can choose the increments from a 3-point distributed random variables where the probabilities for the different values are given like this, and the other supporting values can be given by these 2-point distributed random variables. As an example of a weak order 2.0 method, we present here the butcher tableau for a method presented by Andreas Dressler. This method is rather complicated to write out. It's written out in the lecture material, but it's quite nice to use in the end. And these methods are sort of such that you need to implement them yourself to actually get a hands-on view on how to use them. But luckily, this will be considered in the exercises on the course. However, now to give you a nice example of where these weak order Runge-Kutta methods can be used, we consider the Duffing-van der Pol oscillator once more. So you recall from the previous part of the lecture the model for the Duffing-van der Pol oscillator, and now we are not interested in the solution trajectories in this example, but we consider solution trajectories that start at a given point. The point is -3, 0, which was sort of like in between the solution trajectories, or in the middle part of the solution trajectories considered earlier in the example. We use the stochastic Runge-Kutta method of weak order 2, presented just on the previous slide. And now we can consider a slightly larger step size. So in the previous example we had of this model, we used the step size of delta t equaling 2 to the power of -5. Now we have a step size of 2 to the power of -4. And what we are interested in this example is the histogram of solutions at time t equals 20. So basically we are interested in where the solution trajectories end up after 20 time steps. We simulate 10,000 samples using the weak Runge-Kutta method, and it's worth noticing that with the delta t this large, the Euler-Maruyama method does not provide any useful results. So now we sort of save some computations by using a higher order method with a larger step size. So this is the problem setup, and these are the results when we use the given weak order 2 method for simulating solutions from the model. And here we see that as expected, the result is that it's quite likely that we end up in either of the fixed points, which were at -1 and 1, and in this case it's more probable to end up in the point at 1. So now we were not interested in the actual trajectories, but in the distribution of the solutions at a certain time point in this case. Now, after going through some ordinary Runge-Kutta methods, some strong stochastic Runge-Kutta methods, some weak stochastic Runge-Kutta methods, it's time to summarize what we learned. Stochastic Runge-Kutta methods are basically derivative-free methods for solving SDEs. Solving here, of course, means simulating trajectories or solutions from the SDEs. It is important to remember that these methods cannot be derived as simple extensions of ordinary Runge-Kutta methods, even though the derivation of the methods resemble each other. Also remember that you cannot get rid of the iterated Ito integral. This causes some complications for the strong order schemes, but in the weak order schemes there are remedies for this. The complexity of the methods grows with the approximation order, but the approximation order can also provide a remedy in the sense that you can use larger step sizes. Higher order schemes can be practical for models with some special structure, meaning like scalar, additive, commutative noise, etc. In those cases, you can throw away some terms and still be left with a higher order method, which can be used with a quite long step size in some cases. The choice between using a weak or strong scheme depends on your application and what you're interested in. Basically, if you're interested in the solution paths as such, or just the distribution of the solutions. As for any numerical methods, like the best way to learn how to use them and to understand how they work is to implement them yourself. And that will be the topic in the exercises regarding this lecture.